Welcome back, everybody. We are here. We're going to talk now about the AC induction motor, our squirrel cage motor. And we're going to start this off, like we talked in the last video about um, the single phase versus polyphase or three phase
Phase. Yeah.
induction motors. Um, we're going to talk about the more complicated first because it makes a little bit more sense, because in order to get the more simple, the single phase done,
Yeah.
there's a lot more that you're going to have to do in order to keep it rotating.
Yeah. So, if we're talking about an AC motor, a squirrel cage AC motor, we have to kind of keep in mind that we've got the stator and the rotor respectively, right?
Yeah.
And when we're looking at this, the ultimately what we need is we need to find a way to generate effectively a rotating magnetic field that we can use to induce a corresponding current and magnetic field on the rotor, and we'll talk about like how that works in just a moment. But if we're looking at the stator's role in an AC induction motor is to generate this rotating magnetic field.
So in other words, nothing is actually physically rotating in this, but what is rotating is that magnetic field.
Right. And if you think back to the kind of sine waves for like a three-phase power system, right? They come in at they're offset from each other at different angles, 120 degrees.
Yeah.
Which means like if they're peaking at different moments in time, you kind of have this.
The magnetic induction that happens from that is peaking at different times as well.
Yeah, which means that we have a magnetic field that is changing in strength around the perimeter or around these field windings. And so on the diagram on the right, you can see that we have this rotating magnetic field that's like a spinning north and south. That's the combined effect of the diagram on the left.
So on the diagram on the left, you have those three offset 120 degree phase angles of the three phases there, and you can see what is happening to the magnetic attraction to these different poles. Is what you see there in the middle.
Yeah.
They grow as current peaks on each one.
Yeah. And so this behavior is what generates like this effective rotating magnetic field, if you will, in the stator. And so we use this in combination with the rotor to actually make this work. So if we're looking at this from just like a components perspective real quick, the stator is essentially the housing for the motor in this case. And the rotor is that thing that we see pulled out of the motor.
And unlike, a permanent magnet DC, or a field winding magnet DC,
Yeah.
there are no wires going to the middle,
No.
which makes it extremely cheap to produce.
And it also makes this very mechanically reliable. There's almost no maintenance on these motors.
Yeah. And what you see there is those sort of bars that are going across. That's the squirrel cage that they're talking about.
Yeah.
It's just a descriptor for what that is, and it's aluminum bars that create eddy currents when induced, and then surrounded by steel.
Yeah.
Or iron.
Iron. And
Which allows magnets to conduct through them, and so
it's that same concept we've seen in the applications for like the field windings of a DC motor and the armature. Like we have this ferrous magnetic core that's used to enhance this effect
of the magnetic field on that. And so that basically, without having any actual the induction that's happening on this is essentially grounded out. This is sort of the magnetic pathway to ground.
Yeah.
And this causes the alternating aluminum and iron core is what causes it to spin within that rotating magnetic field.
So if we look at this, we're kind of keep this concept in mind that we were just talking about, because this is fundamental to how these motors behave and how they work.
Yeah.
So if we're going to look at this stator here, The thing here that what we're really doing is that as that magnetic field is rotating, remember that any time that we have a moving or changing magnetic field in the presence of a conductor, we're going to induce voltage and current flow through that conductor. Current flow if we have a closed circuit, which we do in the case of the rotor, and we're going to look at its specific components here. So if we take out the iron core, all we're essentially left with is this structure that is like two rings with these aluminum bars that are running lengthwise across it.
Squirrel cage.
It's a squirrel cage. If we induce a voltage, if we put this squirrel cage in the presence of a changing magnetic field, we're going to induce voltages on these bars, and because they're connected to one another through those metallic rings, we have a closed circuit. And so that means that we're going to get current flow through this squirrel cage as that magnetic field is moving, which in turn means that we're going to generate a corresponding magnetic field that will be of the opposite polarity, which in turn gets us back to that position we were at with the DC motor.
With the repulsion and
attraction.
Attraction. And what that, like, so that circuit though is self-contained on this.
Yes. It doesn't require external brushes to come in and make it work.
It's essentially just a loop that it's following around that squirrel cage like a squirrel within its cage.
Yeah. And so here's a diagram. I would recommend that you take a moment to absorb this diagram when you guys have a chance, but it kind of lays out the relative position of the magnetic field from the stator relative to the direction of current flow and polarity of the magnetic field on the squirrel cage. And that you can see that if you look at this, the direction, like these are setting up that relationship we were just talking about, where we're going to have a portion of this that is pushing away and a portion of this that is pulling towards those corresponding magnetic fields. Yeah. So that brings us to motor speed and the speed of induction motors.
So we've got this rotating thing that has to do with the three phases that are offset from one another.
Yeah.
And the thing is that the induction speed has to do with the frequency that's coming into it and the number of connected poles. So, and essentially, poles, just like a magnet, it's basically how many field windings we have in there.
Yeah.
And the more field windings we have in there, that splits up the total circle, the total pie that we have here, into smaller slices, which means that if it goes through three phases and it's got more poles,
Yeah.
that means it will go through less of the arc in one cycle. And so it actually, the more poles you have, the more it slows it down.
Yeah, and one of the things to point out here is that the diagram that we're looking at right now on the right-hand side, this is for a two-pole motor. The number of poles a motor has, is we're saying that's how many poles per phase.
Per phase, yes,
of that motor.
Absolutely. So like it has 6 windings in it, clearly.
Yeah.
But it's 2 windings per phase.
Yeah. And so and just like Jason was saying, is that depending at like the angular position of these poles is what ultimately drives how much the rotor is going to spin kind of per pulse or per cycle of our frequency input or AC or AC sine wave.
So here's where we can really see the difference here.
Yeah.
You've got your 2-pole motor over there, so it's 2 poles per phase. And then our 4-pole, we're cramming twice as many in there, right? We're cramming twice as many windings within there. And so that means that in order for it to go through one single like cycle of rotation, we're talking about it going around only halfway.
Yeah. And remember, like the relationship here between these poles is like the red pole, like if we're looking at the center here, right, we've basically gone from an angular difference between 2 sets of poles of like 30 degrees to essentially like 15 or 20 degrees, however, whatever that works out to.
So, and you know, it is like a normal thing, like, okay, why would you make the motor slower? well, you might want it to spin slower.
Yeah.
But you're also gaining something from that, because by packing these in tighter and giving them more proximity to pull through, you're actually increasing torque.
Yeah. And at the same time, you're also smoothing out the transitions between these different phases.
So there's a different noise that you're going to
Yeah.
hear from a 12 pole or a 6 pole motor than you would hear from a 2 pole motor.
Yeah. A 2-pole motor has a very particular sound when it's on, and they vibrate, and they sound different from higher pole motors.
Yeah.
And that's actually something to keep in mind when you're troubleshooting a motor, or when you're looking at examining a motor to see if it needs maintenance or something's wrong with it. The sound it makes is often an indicator of
Yeah, and if
how healthy the motor is.
Like, so you need to relate, like, oh, this is a 12 pole motor, and it's sounding like a 4 pole motor.
That's not good.
That's not good. That
Yeah.
means that something's like a bearing's going out.
So let's talk about speed of induction motors, because speed is directly related to frequency. So the frequency input you put into an induction motor is going to give you a specific RPM at the output.
Because that's really the speed of that rotational magnetic field.
Right. And so here, the easy way that you do this is you basically take your frequency, you multiply it by 60 seconds or a minute, and then you multiply it by 2 pulses. And then you end up with, if we're in North America, we
Because there's a positive pulse and a negative pulse.
Yeah. We end up with 7,200. Then we divide that by the number of poles, and that's going to be essentially the actual like synchronous speed of the motor.
Yeah. And we say synchronous. None of these motors are synchronous.
We're going to talk about.
We're going to talk about that later.
We're going to talk about what that means later. But from a general rule of thumb, your 2-pole motors, in reality, you're not going to see 3,600 RPM if we run this for a 2-pole motor. We're going to see something that's closer to like 3,400 RPM, maybe
under the typical load. So that's the number you're going to see on the plate as like the
you'll see
nominal
speed.
And that's basically assuming a certain load for it. For instance, like, you've got a load that's going to require a 1/4 horsepower or a half horsepower or a full horsepower.
Or 100 horsepower. Like it does, like that doesn't.
The synchronous speed is never achievable. Even like there's still a little bit that causes slip in there because of the friction due to the bearings, and we'll get to the slip. We're talking a lot about it, but like you got to get through this stuff in order to understand what's actually subtracting from it.
Yeah. So 4-pole motors, the typical load RPM is going to be somewhere around 1725. It might be 1750 depending on the motor, that type of stuff. It's going to be around there. What this means, though, is that like if you can just memorize these RPM values and directly correlate them to the number of poles that are going to be in a motor.
Yeah, and it's worth reading these right here just to kind of wrap your head around the types of applications we use each of these in.
Yeah.
6-pole motors, again, we get another reduction in RPM to 1,200 synchronous, but like in actuality, 1050 or 1175 loaded. And then 12 we get down to 600, and then 16
down to 400. And like reality, you're probably like, if you're at 16, your real world speed is probably somewhere around like 400 or 375.
Yeah, and we don't want ceiling fans spinning very fast if you look at that application there. Nor do we want them making much noise.
Yeah.
The more poles we have, the less vibration, the less noise that they generate, and so that's an additional benefit there.
And a ceiling fan doesn't need a lot of torque, but we're still utilizing a 16-pole motor because a 16-pole motor is very quiet.
What it means is that you can get away with a lot smaller windings, so like because you get such great torque out of that.
Exactly, and so for that application, it can actually be much more energy efficient to utilize a 16-pole motor in that application rather than a 2-pole.
Yeah.
So when we keep this in mind, keep this concept of like frequency has a direct correlation to speed with every induction motor that exists.
Yeah. And there's also like in addition to that, like you've got the higher the RPM, the higher the noise. there's an additional component to the noise that you hear, and that is the fact that, you know, if it is pulling between longer distances, it means that there's an asynchronous there's an asynchronous nature to sort of the velocity. There's a lot more wobble in the velocity naturally because it's at some point farther away from the thing that's attracted to or repelling from, and so that means that you've got this sort of
There's more vibration,
wobble and vibration to lower pole motors.
Yeah, which is something that may become critical in certain applications. But it also is something to be. It's also part of the reason why these different pole configurations have different auditory signatures.
Sound, yeah.
Okay, let's talk torque, because this is different than a DC motor.
Yeah, we saw a straight line there.
Yeah, we do
Now
not.
we got squiggly crap. What is going on?
And like, why? Like, how is torque suddenly like peaking like at nearly our rated RPM? That doesn't make any goddamn sense.
Yeah, and it just has to do with
Pardon my French.
I mean, it has to do with the fact that when we're dealing with this rotational magnetic field, it's kind of got to come up to speed. It's not going anywhere near its full speed, even though the moment you energize that magnetic field, the magnetic field is going at that speed.
Yes, there's a lag between the rotor and the actual.
The rotor has to pick up the momentum to follow physically that. And what's happening is it's slipping a lot at the beginning. And then it eventually catches up. And then as it's slipping less and less, we get higher torque over the top of it. So you're kind of getting through context here, hopefully, the beginning ideas of what we're talking about when we're talking about slip.
So one of the things that you'll see is that, like, we get this peak right before our maximum kind of rated RPM, and then like
that's the synchronous RPM.
Yeah.
So that means like that's where it stalls out.
Yeah. If you hit synchronous RPM, like there's no longer any torque available for you to
at all.
Yeah. Which is why an induction motor technically always has some amount of slip to it.
Yeah.
Unless you lock the rotor.
Also, look what's happened to current there.
Yeah, current has also dropped off a cliff.
Right. Yeah. Current is approaching zero.
Yeah.
Is that ever like a motor is spinning at its fastest and then it got it's drawing 0 amps?
What is that about?
Well, it's not able to do anything with it.
Yeah, exactly.
Right. So like it reaches this sort of impossible phase there.
Yeah. We'll get into this in more detail when we continue on here a little bit, but we've finally kind of come to this concept of slip
that we couldn't not let slip before.
Ha ha ha.
You can punish me later.
The puns are flying fast and thick today.
So slip is defined as the difference between the flux speed, which is the speed that rotational magnetic field is going, and the actual rotor speed.
Yeah. And so so keep in mind, the rotating magnetic field the stator is generating is effectively rotating at a certain RPM, right? And that's going to be 3,600 RPM or
it's essentially defined by what you've got coming out of the wall and how many how many poles you've got in the motor.
Yeah.
And that's instantaneous the moment you plug it in. And so when you think about that, it an AC nothing goes from 0 to 100 and nothing flat.
Yeah.
And so at the beginning there's a lot of slip. It's stationary and the magnetic field is already rotating at 1,700 RPM.
Yeah.
In a 4-pole motor. And so what do we do there? We've got to it's going to come to a process of catching up. And then if it's also carrying a load behind it, that load is going to make it lag behind.
Exactly. And the more load you apply, slip increases up to a certain point.
Yeah.
But there's a limit to this with induction motors, because we need to, you kind of need to stay inside of this sweet spot for the motor to be able to do what it needs to do. And if you exceed that, then the motor essentially immediately stalls.
and it starts drawing way more current.
Way more current.
Because when it's standing still,
Yeah.
that's when you draw the most amount of current on these windings.
Yeah. And this is a behavior that you will see with induction motors when you turn them on, that there's this initial spike of inrush current that happens every single time.
Yeah.
And that's because the rotor is not spinning.
Yep. And you've seen this all, at home. You maybe
Turn a
noticed,
vacuum on.
You turn a vacuum on and the lights dim. That's what's happening. Is that like you're drawing a lot of current as you start up that motor. Likewise, if your refrigerator compressor starts going, or if your AC
Turns on,
turns on.
You frequently see like your lights dim, and
Yeah.
that's because the motor has not gotten up to speed, and so it draws an enormous amount of current for a very brief period of time. But it's still like we're talking like 3 or 4 or 10 times the rated current that the motor would typically draw.
If we exceed the max load that we have on this motor and it stalls,
Yeah.
right, we're drawing it back to that high current stage, and we can really damage the wires in the windings of it.
Yeah, and because we essentially go like thinking back to like the fundamentals of induction, right? And this concept of this changing magnetic field. If suddenly we no longer have something that's acting as a resistive element in that, the amount of current that will flow through a conductor in the presence of no resistance is infinity. And so you will literally melt the windings of a motor.
Yeah. By holding it and standing it still.
Yeah.
So yeah.
So that kind of brings us to how do we solve this for single phase? Because we kind of have this figured out for
I mean, it's
polyphase.
super easy with the 3-phase, right? Because you've got like every time one's peaking, another one's dipping. But how do we deal with a single phase? If we look at it here in this diagram here, it is switching back and forth between north and south, but it's doing that on like opposite sides here.
Yeah, and it's like synchronized.
It's synchronized. Like, how do we deal with that?
And we need a difference to actually between like those two portions to actually get this thing to rotate.
Yeah, and so otherwise it just sit there and buzz.
Yeah, which is a very distinct sound when it comes to an AC motor.
Right, it is.
So if we
give the motor a push so that the rotor has a bit of momentum,
yeah,
it will continue to spin in that direction because it's constantly running against the same alternating cycle.
yeah,
Right. So the way that we do this is we add capacitors.
Yeah.
We add an additional winding that we don't use after the motor started, but we add windings and a capacitor that is charged off of that single phase. And that capacitor is going to lag behind it. We'll get into that in the AC panel building class.
Yeah.
But that capacitor is going to cause a lag in current, and that's actually going to cause that to be offset and create a second phase.
Yes, and this second phase will be there kind of temporarily, and the way this typically works is that there will be some type of centrifugal switch that basically opens this, breaks the secondary winding away from the main motor windings after a certain RPM. So when the motor is at low RPM or stopped, this switch closes and we engage this capacitor-driven field winding.
Yeah.
And it creates this offset polarity field that we can use to give us our initial push. And then once we get up to speed, the switch opens and it takes it out of that circuit.
Yeah. So I guess the long and short of it is it works much the same way. You can have the same
fundamental principles are still at play.
Number of poles in there,
Yeah.
et cetera, et cetera. But the difference is really that you only have with 3-phase, you've got much more constant torque.
Yep.
And you also, when you think about it, we've got all of that copper from the windings that we only use when we're starting the motor on this one.
Yeah.
So it's a little bit wasteful and inefficient.
Yeah, and even when the motor is running, it's still less efficient of a design than a 3-phase motor overall, not just from like the material usage, but also from like an energy transfer perspective.
Yeah.
It is a less efficient design.
Which sucks because none of us have three-phase at home,
Yeah,
right? All of our motors are going to be this lame
single phase thing. Like
design.
so, like your washing machine, your like if you have
Your dryer,
your dryer, all of these things that use large AC motors that require like your 240 volt outlets. They're all these.
Increasingly, those are brushless DC,
But
which gets around that.
Which gets around that. But like if you have something that's like an appliance that's from the 90s,
Yeah.
it's one of these motors.
Or if you've got if you've got a table saw, or if you've got a bandsaw, or any like power tools that run on a single phase AC motor, that's kind of that you've got.
Yeah,
here.
like so circular saw, that's wall driven.
Yep.
Most likely it's one of these.
Yep. Yeah, exactly.
So
here's a YouTube video to like kind of go through what you find on the nameplate of a motor. It's a little dry, but like it's an important thing to be able to recognize. So please watch this video in your own time.
Yeah.
And we're going to take a break here, and we're going to come back in another part of this video. And yeah.
Yeah. So we'll see you guys in the next video on this, and we're gonna wrap up our discussion on AC motors.
Yep.